My name is Steph Evans and I'm the lead FEA engineer at Evotech CAE Ltd. This video makes up a tutorial from the 101 series and is focused on a number of aspects of 3D hexahedral element modelling and FEA within Apex. Okay, so in this example we're going to look at some 3D modelling and analysis with hexahedral or hex elements. So for the first exercise we're going to build some geometry directly within Apex, so this hasn't been brought in from CAD, so we're looking at some of the sketcher tools. So we're developing a rectangular surface based on predefined dimensions, putting a circle on the front of the surface. Ultimately we're going to be developing a double lap shear joint using three-dimensional hex elements. So some of the simple sketcher surfaces can be extruded up into the third dimension to give us a piece of solid geometry, and you can see in the tree the solids defined. We have the concept of mappable geometry, so whether we can map geometry for resultant hex meshing. We can set the color, and if the object is green we can hex mesh. If it's red we can't. So it's all about controlling the geometry to give us an assembly or definition that can be hex meshed as required. So we're just punching a hole through the center of the solid, and again we saw there that the geometry is green when we put the 2.5D mesh type on, and as soon as we put a fillet onto the geometry, so it's no longer mappable geometry, the structure turns red and we can't hex mesh that directly. So defeaturing that solid, we can see, simplifying it, goes straight back to green, and we can hex mesh this in 3D if necessary. So going into the 2.5D meshing tools, so setting an appropriate element edge length, and we can develop the mesh very quickly. We can use the concept of the 2D surface mesh as a surface seed, again using an appropriate element edge length, and with some of the feature mesh washer settings we've got a series of uniform element rings around the hole. Then 2.5D meshing to develop the 3D hex mesh state, and we can see now we've got a very nice mesh definition at the hole and good quality element definition elsewhere. So we put the element checks on, or element quality fringe plots on, we can see that we've got good quality elements everywhere, and there's no issue with that definition whatsoever. Again, using the direct modeling geometry engine, we can push-pull the geometry with a live update in terms of the remesh and the element quality, so very quick to modify and amend the geometry and the underlying mesh. So again, double lap shear joint that we're going to be analysing or developing first of all. So using the transform tools in Apex, copying the entity solid geometry with mesh up a couple of times to give us 3 discrete plates. Going to colour the discrete plates so we can see the separate entities, turn off the geometry, and we can see the assembly starting to take shape. So using the transform tool in Apex, this time we're going to rotate the middle plate by 180 degrees, move the transform tool to a node which we've created at the center of the hole, and then switch to rotate mode 180 degrees, and we've got our double lap shear plate definition. So continuing with the assembly, we've done some more sketching tools and extrusion, push-pull, etc. to develop a fastener, a three-dimensional fastener between the plates, and we can see we've got an assembly with discrete parts set up in the browser tree. We've glued the pin or the fastener to the surrounding plates. I should note that we haven't glued the plates themselves together. That would defeat the purpose of the double lap joint. And shown in wireframe we can see the fastener and how it protrudes through the assembly. and we can run an analysis. In this instance we've used a linear static analysis, but we could use non-linear tools if necessary, depending on what we're trying to achieve. So looking at some perhaps more complex real-world geometry, and again this is going to take the form of a target for hex mesh definition. You can see that we have quite a bit of detail in the structure, and if we turn the 2.5D colour on, we can see that the structure goes red immediately. There's no way in its current form that we can hex mesh or 2.5D hex mesh this structure, and in fact if we try that, there's a warning message to say that the geometry is not suitable for that operation. So we need to do some initial geometry cleanup within Apex to simplify the geometry, and then to leave us with a form that we can hex mesh. So using some simple defeaturing tools, we can do it on a manual approach, or we can use the auto defeature by selecting the solid and allowing Apex to highlight all of the three-dimensional features which we want to get rid of. So it's highlighted some fillets and some chamfers. So if you'll notice, in this model we have a number of different fillet dimensions. So we have some larger fillets at the base of the clamping plates, and we have much smaller fillets at the tube intersection, and even smaller fillets again at the bosses which protrude out for locating pins. So we can control the selection of the features and only remove the features of a given dimension that we want to get rid of. We can leave everything else that we know we can live with from a hex meshing perspective. So taking out the chamfers as well, so we've now got a much simpler form. We've got some locating spigots on one of the faces, so we're going to remove those just by a simple push pull up to operation to smooth them off with the underlying face. And now we're in a position where we can start to understand how the geometry will work from a hex meshing perspective. So using the split tool, we can start to break the solid geometry up into a series of mappable surfaces for the resultant hex mesh. Just to highlight first of all the raw split tool, as it were. So that takes the original solid and splits it about a face, and you can see we end up with two target solids left for the operation. We're going to undo that because we don't want that for this particular operation. What we want to do is partition the solid geometry so that we have a single solid, but with a number of partitions within there, which can be used for discrete hex meshing with a common congruent boundary at the interface between the partitions. So you can see if we turn the element topology, or rather the geometry topology lines on, we can see how the split has occurred. We've still got a single solid within the browser tree, and if we turn the 2.5D coloured display on, we can see we now have the makings of a green region which can be hex meshed. Obviously the rest of the geometry has not been partitioned and is so quite complex still. So again, using the partition split tool with faces and surfaces, we can start to break the solid down into discrete partitions which can be hex meshed. And again, now we've got the whole structure turned green, a single solid in the tree, so we can hex mesh with congruent faces. So looking at the 2.5D meshing tool, putting in the appropriate element edge length, and taking pretty much the default parameters for the mesh definition, running the operation, and we've got the hex meshes hex elements defined for a single hex mesh. The structure is fully tied together even though it's partitioned, and we can look at the element quality. If we remove all the good quality elements, we can see we have got some areas of interest where the quality is perhaps not what we want it to be, certainly at the upper face of the clamping plate. So poor and even bad elements in there. So what we're going to do is delete the original mesh definition and use a 2D surface to seed the hex mesh in that location. So going back into the surface mesh tools, again with a similar edge length, default mesh parameters, pick the face that we want to mesh. We've now got a 2D mesh on that face, and we can have a quick look at it. We've got a nice ring of elements or washer around the holes. We can check the quality if necessary, and then we can go back into the 2.5D meshing tool to develop the hex elements, and now we will have a much better definition in terms of element quality at the area where we've controlled the resultant hex mesh with a surface seed. So if we remove the 2D elements from view, and we've got rid of the bad elements around the area where we were controlling the mesh. We do have some other not exactly perfect elements, but we're not too concerned with that in this particular situation. So coming out of the hex mesh, we can now delete the surface seed mesh, or the 2D element mesh, and we're left with the underlying 3D mesh and again the element quality. So again, different techniques we can control the hex mesh in a given region. So we're now going to put an edge seed around a hole, and you can see the live update of both mesh and element quality based on the seed, and we can do this for any area that we're interested in and effectively start to improve the mesh definition as required. So turn the element quality off. So we're pretty much done with this now from a hex mesh perspective. We can do some quick checks for cracks in the mesh. We have no cracks. We can show element topology based on the edges, similar to the geometric display, so we can see the shared edges around the boundary of the structure. And the key thing here is that because we've partitioned rather than split the solid, we have a congruent mesh for the full model definition. So just to demonstrate why we go through this process of simplifying geometry to develop a hex mesh, if we compare the model definition with effectively the starting point geometry, which we've hex meshed with default mesh parameters and an equivalent element edge length, because of the formulation of the tetrahedral element compared with the hex element, we end up with a model which is significantly different in terms of both node count and analysis time. So the blue mesh on the left, and again shown on the pie chart, is much smaller in terms of the overall model size. And then if we run the analysis for a typical load case, depending on what we're trying to achieve from the analysis, we can see that in terms of the accuracy, we've got a very, very good tie-up between the hex mesh and the underlying tet mesh, but with a massive decrease in terms of computational cost and overall analysis time. Okay, thanks for watching this tutorial. Be sure to keep an eye out for the remaining tutorials in the 101 series to illustrate how Apex can help with your FEA process.